Professor Syed Farooq Ali, start your talk, please.
Yes, yes.
And share your screen first.
So, am I audible and my screen is visible?
Yes.
And I'm navigating my slides. Is the slides are being navigated as well as being shown
Yes.
to you? Okay. So, my name is Syed Farooq Ali. Uh, uh, the title of my presentation is Human Posture Recognition Using Robots Based on Spatio-Temporal Features, along with radon transform. So, the overview is just I would explain the problem and its applications, facts and figures that highlights the importance of this problem, contributions which we made, data sets we used, methodology that we proposed, results, conclusion, followed by our publications which we did. So if we explain the problem, we want to make an intelligent camera that automatically recognize and classify the postures of a human, including standing, walking, falling, lying, moving up, moving down, crouching, sitting. So these are the postures in which our work has been done. So as picture is better than 1,000 words, so 100 words. So I would like to explain my problem using the picture. So we have this is an MCF data set, and we took the keyframes just to explain the problem. This is a person who has fallen on the ground, and this is sideways slip. And then this is a person who was moving forward, and then it fallen on the ground, and while his mouth and face is towards the floor. And this is another person who was moving and then fallen sideways. Similarly, this is a person who is sitting somewhere, so it is a sitting phase. This is a person who is again fallen. This is a person which has a backward flip. He fallen on the ground while having a backward flip. Similarly, someone can have a forward flip and can fall. So this is a person who has fallen on the ground. This is a crouching. This is a person who is sitting and trying to pick a book. So it is a posture. Similarly, there are postures like crouching. So our research, our work helps to classify different types of postures, human postures. So these are different postures. If we combine them, like person is having a backward flip, the person is sitting on the ground, the person is trying to have a jump, the person is in the state of falling, it was standing, but it is about to fall. This is a person who has already fallen. This is a person who is standing while his hands are towards the ground. So we want to classify these postures. So there are many applications to this problem, including yoga, cricket, gym training, and old people homes, medical health facilities. Uh, the problem why we started this problem was that human falls are the third major cause of unintentional deaths. Around 31 billion per year. The cost of falls is around $31 billion per year in United States. And normally these falls involve men over 65 years of age, and world population of elderly age 65 years is increasing. So it is expected to increase from 901 billion to 1.4 billion by 2030 and to 2.1 billion by 2050. So these are the figures, facts and figures, which are showing that number of deaths are also increasing in different states of United States. So the contribution in our work is that we proposed an algorithm that uses scale invariant features, and we also added a radon transform that captures the human shape deformations. And if we apply the radon transform to an image, it gives us a sinogram. Sinogram helps to uh, capture human shape and human shape deformations. Its value changes when we have a from different posture from one pose to another pose. So we actually use handcrafted features, a lot of scale invariant features at the same time, apart from using radon transform, and we classify it with J48 and ADA boost algorithm. So data sets we used was 4 datasets, MCF that has 24 videos and 8 camera positions. So there are 192 videos because this dataset was taken using 8 camera positions. So 8 cameras were making a video so from different positions. So total 192 videos. Then there is URMD dataset, card, and nuclear. So these datasets we used in our proposed approach, and our proposed approach outperforms the existing approaches. So these are again the key features of all the 4 datasets: keyframes, MCF dataset, URFD dataset, card, and nuclear. And so our phase 1 consists of we we calculated the background, estimated, and try to create a human silhouette. And then we actually the phase 2, which is geometric feature extraction and feature extraction using radon transform, and the phase 3 is we applied the error boost and J48 classifier. Actually, we used all the classifiers in which error boost and J48 was giving the best results because boosting the J48 classifier worked in our favor because of changing the weights and giving us the better results. So this is the description of our whole algorithm. In the left side, we took the frames and then we calculated the background estimation. And after we calculated different background features, we actually extracted this human silhouette from the background. And then we use different features like aspect ratio, geometric centroids, shape descriptor features, ellipse axis ratio. Ellipse axis ratio is we try to fit an ellipse over the human silhouette and try to find the difference between its major axis and minor axis of the ellipse. Silhouette angles, silhouette speed. So we calculated silhouette speed using motion vectors. After calculating these, we also calculate the radon transform and calculated the sinogram of an image. And once these features are calculated, we actually combine these features and gave it to the classifiers, in which we use ADA boost. We boosted the J48 classifier and got the results. So in general, we use aspect ratio, shape descriptor of upper human silhouette, and geometric centroid of human silhouette. We used ellipse axis ratio. We use silhouette angle. Then we use the speed. Then we use the feature extraction using radon transform. So if we see over here, so upper human silhouette means that we try to fit the bounding box, and we take the upper half of the bounding box and calculated the number of ones, the area of the silhouette. If the area is lesser, it means the person is standing. If the area is uh, high, for example, here, this bounding box, if we take the upper half of the bounding box, the area of a human silhouette will be higher. So we will say that this person has fallen. Similarly, we use geometric. We use geometric centroid of human silhouette. So we calculate the centroid of the silhouette, and if the centroid is above 3 feet, it means the person is standing, or if the silhouette is around less than 1 feet, it means the centroid is less than 1 feet. It means that the person has a fall. So, and similarly, ellipse axis ratio. We try to fit the ellipse on a human centroid, on a human silhouette. After fixing the ellipse, we calculated the major axis and the minor axis, and the ratio of it gives us the ellipse ratio. And after calculating the ellipse ratio, it also makes it scale invariant, because ellipse, the ratio never changes, even the camera moves away or closer to the human body, so it remains scale invariant because ratio don't change. Silhouette angles, the angle with this human silhouette makes with the floor, in this case it is making a 90-degree over here. This person is fall, and this is making the angle which is 0 degree. Okay, so with the change of angles, we can definitely calculate these. And then we have silhouette speed. So when a person is moving, it is moving with a lesser speed, but when it falls to the ground, the falling speed becomes very high immediately for a fraction of a second, and with that increase of speed gives us an idea that a person is fallen to the ground. So motion vectors or silhouette speed plays an important role. The feature extraction using radon transform. So we have a radon transform, and we calculated the radon transform, and that gives us different value. So these are the number of frames. So we calculate the standard deviation of various features and of last 25 frames, and these are the values. And when the fall comes, the value changes significantly. For example, geometric centroid of x-axis, geometric centroid y-axis, silhouette speed x-axis, silhouette speed y-axis. So these values are changing significantly. It means with the change of values, uh, uh, with the change of significant values, it becomes easy for us to detect the posture. And then this is the radon transform. How to take a radon transform? So if this is an image and we sum the pixels across, let's say 45-degree, then we will get an array of sum of pixels, and that will be added as a sinogram. So this comes under the Fourier slice theorem. So we will have a sinogram where sinogram will have 180 rows. First row corresponds to 0 degree, second row corresponds to 1 degree, third row corresponds to 2 degree, and similarly the last row is 180 degree. So if we have a theta is equal to 45 degree, and we are we are summing the pixels in this direction, whatever the value comes, we will put it in the sinogram of 44th row. So that's how the sinogram is taken. It works on a principle of Fourier slice theorem. So this is a sinogram of a person which is like this. This is a sinogram of a person in which it is standing. This is the sinogram of a person who is fallen on the ground, and so on. So sinogram changes with respect to the posture, which helps you to identify it in a better way. So now we have results. If we go over the results, first of all, we have completed the ablation study, the relevance analysis of this whole study, because we use all the features and we tried to remove the feature one by one and checked if accuracy is uh, also decreasing or not. So when we change the standard deviation of ellipse ratio, the accuracy decreased for MCF dataset, for nuclei, and for URFD dataset. It means standard deviation of ellipse ratio is an important feature. Similarly, standard deviation of number of zeros, for standard deviation of number of zeros, when we remove this feature and calculated the accuracies on these four datasets, we realize that the accuracies are being reduced, are decreasing when we reduce this feature. Similarly, when we remove the feature standard deviation of motion vector, the accuracies of and we calculated the accuracies again on these four data sets, the accuracies were lesser than the as compared to when this feature was added, which means that this feature also has a significant role in the value in the results and in the accuracy. Similarly, standard deviation of bounding box or standard deviation of fall angle, standard deviation of centroid and aspect ratio were removed one by one, and we realize that the accuracy is also decreasing, which shows that each of these features are relevant and important. So if we go over the results, so we calculated the results of our proposed approach. Uh, we calculated the results of a proposed approach on four data sets, and we got different results. So our proposed approach gave 98.2% accuracy on MCF dataset when 8 postures were used. When 4 postures were used, the accuracy increased to 99.7 and so on. So card, nuclear, and URFD datasets gave us this accuracy, and we can see clearly that we made a comparison with 9 state-of-the-art existing approaches, and our work uh, says that our accuracy outperformed the existing accuracies. And then we compared our proposed approach using accuracy, specificity, and SE. So these three features, and after comparing the accuracies and specificities, we realize that our approach has outperformed the existing approaches. Similarly, we have generated the results for 5 classes of MCF dataset, and again our proposed approach outperformed in terms of accuracy, specificity, and SE. So these terms, similarly, for 2 classes, our approach also outperformed uh, the existing approaches when we made a comparison with around uh, 12 different approaches. Similarly, when we used our URFD dataset for 7 classes for 7 different postures, our proposed approach, you can see, outperforms the existing approaches. And then we generated the results using card. These results are also compared with the existing approaches, and it can be seen that our proposed approach showed significantly better results than the existing approaches. The approach Ali, this was also the paper written by myself, and this and our existing work was improved version of this paper. And then we compared our approach in terms of execution time and showed better results. So in conclusion, at that time we thought to use the handcrafted feature along with the existing deep architectures to further improve the results. And in human posture recognition, using radon transform as a feature gives better results. So it's a good feature which was never being used before at that time. Similarly, fusion of deep features and proposed features also can create better results. And we believe addition of large real world repositories will further improve the results and work in this area. After our this presentation, we published 4 journals. We extended our work for deep architectures, and we published this first journal in which we use deep residual network and produce better results. And then we used this third journal in which this fourth journal in which we also used different features. So, and then we have a conference paper in which we use the deep architecture and also machine learning features to generate better results. So in this area, we are working for last 10 plus years, and we have these publications related to this area. So that is the end of my presentation. If anyone has any question, please ask.
Yeah, thanks, Professor Syed Farooq Ali, for your wonderful presentation. It was interesting to see that how features, hand-engineered features and AdaBoost classification model can also be used. I was knowing that it's mainly the deep learning model or graph convolutional networks which are used for posture detection. But this was another side of the coin, and it was interesting to see your work. If any in the attendees, anyone is having questions, can please ask questions. So in case of no question, I'll proceed with the next speaker. I invite Professor Zhenong Chen from Liverpool University, China, to proceed with your presentation.
Okay, can you hear me?
Yeah, you are audible. Start presenting
Okay.
your screen.
Okay, let me share my screen. Wait a minute.